Welcome everyone to this explainer. Okay, whether you are just brushing up on the absolute basics or you're gearing up for that big lab evaluation, this survival guide has exactly what we need. Today, we are charting the incredible evolution of precision in the machine shop. We're literally tracing the journey from those tactile, hands-on techniques of conventional manual machining, all the way up to the highly automated, code-driven world of CNC. We are going to figure out the mechanics behind the machines so you don't just know what buttons to press, but exactly why you're pressing them.
All right, here's our roadmap for the evaluation. 1. Conventional machining basics. 2. Sheet bending and welding. 3. Foundry and 3D printing. 4. CNC milling fundamentals. 5. CNC milling practical steps. And 6. CNC lathe operations. Let's dive right in.
Section 1. Conventional machining basics, the foundation. Look, to really understand subtractive manufacturing, we have to start at the absolute foundation.
Check out this classic watch and lathe from the guide. In subtractive manufacturing, well, it's exactly what it sounds like. We are taking away material to reveal the final shape hiding inside. Here, the machine removes material from a rotating mild steel workpiece using a high-speed steel, or HSS, single-point cutting tool. And honestly, it is a surprisingly aggressive process. You're physically turning wheels to literally shove hardened steel into softer, spinning steel. It really gives you a deep appreciation for the raw physical forces at play before a computer ever even gets involved.
Now, safety and precision, they go hand in hand here. You want to move those hand wheels extremely slowly. The smoother and slower your rotation, the finer your surface finish is going to be. And the guide points out a massive visual indicator here. Watch your chips. If the metal chips flying off start turning blue or brown, yeah, back off. That means they are superheated, your speed or your depth of cut is dangerously high, and you are absolutely going to burn out your tool. That is the machine's way of screaming at us to slow down.
Moving along to Section 2, sheet bending and welding, joining forces. Let's put away the cutting tools for a second and see how we bend and permanently join metal together. Notice how a totally flat sheet of metal is transformed into a really robust structure. We start with a raw 80 by 100 millimeter sheet. You methodically mark it with chalk and then throw it on this massive 72-inch bed sheet bending machine. You basically pull the bar upward for a 90-degree bend, flip it over, push backward for a 45-degree bend, and then, honestly, you just hammer it flat to lock in a highly precise structural seam. It's a fantastic example of manual, physical manipulation that takes some serious elbow grease. All right, let's break down our three main welding techniques with this table. MIG welding uses gases like argon and CO2 for semi-automatic joints on mild steel. MMA uses a flux-coated rod to stop oxidation while keeping a high-current, low-voltage arc. But look closely at resistance spot welding on the far right. This is super cool. It uses copper electrodes to heat the metal via electrical resistance right to its plastic point. That's right before it actually melts. No flux, no filler metal needed. That makes it an autogenous weld, and it is heavily relied on in the auto industry for lap joints.
Up next, Section 3, Foundry and 3D printing, shaping the future. Let's look at how we create complex shapes entirely from scratch, putting one of our oldest methods right up against one of our newest.
This represents a really fascinating paradigm shift. On the left, FDM 3D printing. It's additive. It literally builds a shape layer by layer by melting thermoplastic filaments like ABS or PLA, which is just fantastic for rapid prototyping. But contrast that with machining, which is totally subtractive. You've got to aggressively carve and remove material away from a solid block to find your final dimensions.
But now let's compare that high-tech 3D printing with traditional foundry work, which is basically the OG additive manufacturing. Here we take what's called green sand, a very specific earthy mix of 75% pure silica, 18% clay for stickiness, and 7% moisture, and pack it tightly into a bottom frame called a drag. We pop in a pattern, place the top frame or cope, and pack in even more sand. Once we pull that pattern out, boom, we have a perfect negative cavity. Finally, we literally pour liquid molten aluminum at a blistering 660 degrees Celsius straight into that cavity. It's ancient, it is very messy, and it is incredibly effective.
Okay, Section 4, CNC milling fundamentals, entering the digital age. Having covered the manual wheels and conventional basics, we have arrived at the core of our lab evaluation masterclass, CNC milling. This is the section you really need to lock in. So to successfully jump from turning manual wheels to executing fully automated, ultra-precise cuts, we have to learn to speak the machine's language. CNC stands for Computer Numerical Control, and it automates the exact path of the cutting tool. But to actually set that path up, we use MDI, or Manual Data Input. This lets you manually punch individual lines of code and commands directly into the machine's onboard brain. And according to the guide, this is the beast we'll be evaluated on, a 3-axis vertical mill. It primarily rocks a super tough tungsten carbon end milling cutter. Notice the ATC right there? That's the automatic tool changer. It uses an air compressor to swap out tools in the blink of an eye. But remember, your very first step will always be clamping down your aluminum workpiece securely to the bed of this machine.
Section 5. CNC Milling. Practical steps. Let's get practical here. Knowing the exact button sequences to run this machine safely is your key to passing, so let's walk through this step by step.
Right, first things first, powering it up. Turn the red knob on the right, then hit the green button in the front. Simple. Next, lock your aluminum workpiece tight into the vise using a number 4 Allen key. Turn it clockwise. Then you'll press the Prog button on the panel and pull up your specific program file. For this evaluation, that's file RKD1. Finally, kick on the spindle to prepare for referencing the x-axis.
Now write these numbers down because they are critical to keep locked in your head. You have to use a feed rate of 100 when the spindle is physically touching the workpiece for referencing, nice and slow to prevent damage. But jump that feed rate up to 1,000 when you're just moving the non-spinning spindle around to place it, just to save time. And when you are finally running the program using the MARS sequence, that's monitor, auto, reset, start, dial your feed rate way back to 30 to 50%. Just play it safe while you watch that first cut happen.
Let's look at exactly how we reference this machine, basically telling the computer where the metal actually is in physical space. Switch to jog mode, move the tool near the left edge, and very carefully touch the spinning spindle to the workpiece. Then, set your x-axis to 0 by hitting F1, then F2, then X, and finally cancel. Next, grab the NPG button, the manual pulse generator, and step the tool exactly 3 millimeters to account for the tool's radius, so your X offset becomes positive 3.00. Once X is locked in, do the exact same touch and offset dance for the Y-axis.
Almost there. Finally, we need our height, the Z-axis. Lightly, and I mean lightly, touch the cutting tool to the top surface by tapping that -Z button. Once it touches, copy that exact reading right into the G54 coordinate system's Z-value slot. Then send the machine back to its home position. Once it is safely parked at home, you execute the automated run using that MARS sequence: monitor, auto, reset, start. Then you just step back and watch your code come to life.
Wrapping things up here with Section 6, CNC lathe operations, turning automated. Just to conclude our CNC instruction, let's briefly shift gears and look at the lathe equivalent of these procedures.
The source material highlights a really practical, operational difference when you jump over to the CNC lathe, step mode versus jog mode. Step mode gives you ultimate manual control. The tool only moves precisely as much as the button is pressed. In fact, if you hold it down, the tool just stops. It won't keep going forward. Jog mode, on the other hand, is your one-click wonder. A single click, and the machine completes the entire facing operation across the metal continuously.
And here is your command center, the CNC 4640 control panel interface. This is where it all comes together. Through this screen, you'll delete old top codes, use MDI to call up your single-point cutting tool, and punch in exact cut diameters. For instance, typing an X value of 25.4 millimeters to get a perfect 1-inch diameter cut. I know it looks like a spaceship dashboard at first, but once you practice those step-by-step sequences, it completely becomes second nature. As we wrap up this explainer and you head into the lab for your evaluation, I really want to leave you with this thought. How does the physical feel of running those old-school, conventional machines, feeling the resistance of the metal, watching the chips change color, how does that actually inform the digital feed rates and offsets you're programming into the CNC? Because honestly, the absolute best CNC operators aren't just coders. They are true machinists who deeply understand how the metal wants to behave. Keep that in mind. Good luck in the shop, stay safe out there, and I will catch you in the next one.